if I don't pronounce it properly. Marcin, Hajduk?
Yes,
Hajduk.
yes. Hajduk.
Go ahead, please.
Thank you. Do you see my screen?
We see it. It is not.
Okay.
Not full mode, Marcin.
Okay. Could it? Because I'm not sure if I can do this in full mode. Could it stay like this, or it's?
It's fine. We can see everything. Yes.
Okay. So I'll talk about the application of a low frequency array for observations of radio continuum from planetary nebula. So the spectrum of ionized shell look like this at low frequencies. It emits thermal radiation and shows a steep slope of the spectral index of 2. And at optically thin part, it shows a flat spectrum. This is a simple formula describing this. This is a Rayleigh-Jeans approximation of Planck curve. And if we go to the optically thick emission, then it's this term in the square is reduced to 1. And if we change it, we can derive the we can determine electron temperature just from the observed flux density and the size of the nebula. So if you have optically thick emission, then we can derive electron temperature derived just from the observed flux. And in optically thin part, radio flux is proportional to H beta flux, because this is similar mechanism. Just in the case of radio emission, electron has a distant encounter, and in the case of H beta, it recombines, so it's close enough proton to recombine. So from the radio flux, we can derive expected H beta flux for this emission. It's slightly dependent on the electron temperature and the chemical composition of the nebula. And if you have an expected H beta flux, you can compare it to observe H beta flux and derive extinction. So low frequency array is a relatively new instrument. It operates on several bases. The core is in the Netherlands, core and remote stations, and there are several international stations. The extent is up to 2,000 kilometers. And one of the most important projects is a LOFAR 2-meter survey. This survey will observe all the northern hemisphere at 144 megahertz. It has a very good sensitivity compared to previous surveys. And I used some preliminary data of LOTS to observe planetary nebula. It has enough sensitivity to detect optically thick emission of planetary nebula. And I have 4 examples here. If we just map the radio emission, we can convert it to electron temperature. So basically we derive electron temperature maps from these observations. And it turned out that for many planetary nebula, the derived electron temperature was much lower than temperature derived from collisionally excited lines like O3. At first, we can consider that the nebula have a temperature gradient. So if in radio we observe outermost layers of the shell, then if there was a temperature gradient, then the radio observations can probe the outermost regions of the nebula and could have just simply derived the lower electron temperature. But optical observations of resolved nebula shows that show that this should not be the case. There could be observed some temperature gradient in the shells, but not that severe like I observe. Another hint comes from observations from recombination lines, because recombination lines show another plasma component in planetary nebula, which has a lower electron temperature of the order of 1000 K or so. And also, if you compare abundances from collisionally excited lines and recombination lines, the abundances of derived from recombination lines are higher. Usually the median, I guess, is around two times higher, but there are some extreme cases in which recombination lines give 100 or more abundances than collisionally excited lines. So another hint is that in radio we observe the mixture of both hot and cold component in planetary nebula. And Garcia Royas presented some observations of this cold component in images, in optical images. We can see that in optical recombination line O2, this cool plasma is close to the central star, whereas in collisionally excited lines, the emission is more extended. So I compared the difference in electron temperature observed from my observations with the electron temperature from collisionally excited lines. And here is the difference versus abundance discrepancy factor. I can see that for high abundance discrepancy, I also observed a big difference between my temperature and temperature obtained from O3. So this supports that I obtain low temperatures because of this cool plasma component. And I did some simple modeling. This blue dashed curve represents just a uniform shell with a temperature of 10,000 K. And this red solid curve represents the case where we have plasma with 10,000 Ks covering 90% of the volume of the shell, and we have just 10% addition of cool plasma with a temperature of 2000 K. You can see that there is no big difference in optically thin part, but in optically thick part, you can reduce the emission by the factor of 2, in spite of the fact that we add only very little cool plasma. And effectively, such a model would emit more or less the same flux as a uniform shell with a temperature of 5000 K. So if you add a little bit of cool plasma, then we can easily observe it in the radio emission. And also, I observed several nebulae which show optically thin emission or partially optically thick. So these are two cases. It's a ring nebula. We can see that the maximum of radio emission is concentrated closer to the center of the nebula than optical emission. In the background, we have H-alpha observations from HST. So this is another case on the right side. In NGC 2371, we can observe also that radio emission is concentrated closer to the central star, but also if you look carefully, we can see that the maxima of optical emission are outside of maxima of radio emission, because these maxima correspond to so-called low ionization structures, which are much cooler than the rest of the nebula. But nevertheless, this difference in radio and optical image cannot be easily explained. Perhaps those low ionization structures do not contain very low plasma, and the rest of the nebula may contain this low plasma component. I'm not sure, because it's difficult to say. And also the fact that we observe much lower electron temperature in radio observations may affect all the research related in which we use radio observations of planetary nebula. For example, we observe the discrepancy between between extinction derived from H alpha to H beta ratio and extinction derived from radio to H beta ratio. So in the radio, we observe lower extinction, but if we assumed lower electron temperature, because in these considerations, people assumed the electron temperature equal to the electron temperature derived from collisionally excited lines, which is not the case. If we decrease electron temperature, this discrepancy would be lower. And also for other studies in which we use radio emission of planetary nebula, we could not simply assume that electron temperature is equal to the temperature obtained from O3 lines. Thank you very much.
Thank you, Marcin. Do we have any questions? Okay, well, people take courage. I can ask you questions or a comment on NGC 2371. So I think there's a slight difference between the radio emission from the ring nebula and these clumps in 2371, because I think these are photoevaporative flows, which are shielding like very cold dust within these clumps. These are not typical low ionization structure. This is my impression, the difference with the ring nebula at least.
So we ask the difference between NGC 2371 and
the ring nebula.
Well, I didn't look very carefully at these cases, but well, this NGC 2371 is a bipolar nebula. What we see in the in optical observations is just a tail, bright tail of the nebula. I think, and there was a specially resolved spectroscopy of this tail, of this shell, but well, it's hard to say what would be the difference, which would affect radio observations.
So we have Bruce Valek. I saw your hand raised. Do you want to ask a question?
All right. I'm a great talk, and I love this stuff. The low frequency radio part of the spectrum has been ignored much too long. My question is this. When we look at the sun, we see the outermost opaque layer, and we measure the temperature in that layer. What you're doing is almost exactly the same. You're looking at the outermost opaque layer in the radio, and that layer may be far away from the inner parts of the nebula itself. So I guess it doesn't surprise me that the temperatures, optical and radio, don't agree, because they're sampling different spatial volumes. I wondered if you could comment about that.
Well, of course, there is, for example, a selection, observing selection in my sample, because I observe mainly young planetary nebulae, which are ionization bounded. So I observe the region, I sample the region close to the ionization front. Well, it's different. I guess the plasma close to ionization front may be a bit different, behave in a different way. I mean, maybe denser and more dense, and I thought that this could affect the electron temperature, but yeah, but the observations show that that optical observations show that the temperature is not, I mean, there is not a strong gradient in electron temperature. So it's difficult to say. I guess that maybe I should do some maybe photoionization modeling to try to understand better the distribution of electron temperature in the nebula. So maybe that would help to answer what exactly I see. And also I plan to observe at different frequencies, at lower frequency and then higher frequency, to see if we can have different temperatures, let's say at 3 megahertz. So I would sample the nebula at different radii, and I would see what happens with the temperature in the outermost part of the shell. So maybe in the future I will be able to tell more about this.
Good answer. Thank you.
Alex Raga just posted here on the chat, like HH objects also reduce the lower temperatures from the radio continuum observation. So I think in those cases are similar as the photo evaporated flows, as I mentioned. So maybe Alex wants to comment on this.
Basically, that in an HH object, the interpretation is that in a shock wave, you tend to produce a collisionally excited lines closer to the shock at higher temperatures, and the recombination lines, as well as the radio continuum in some denser, cooler region far away. This seems to be a natural thing of a shock wave. Of course, not of a photoionized gas. No, this is the problem.
Yeah, and Marcin, finally, I can also comment on this. If you show, when you show the images of your 4 objects, can you show that again?
Okay.
I was puzzled because, in particular for NGC 7027, it seems to be mapping the hot bubble, the X-ray emitting hot bubble. Joel can confirm this. So this goes in the same direction as Bruce was asking. So in general, so this free emission contains, it also contains some emission from different plasma temperatures, or temperature from different plasmas. So you see this 7027 almost maps the hot bubble. And also in the cat-sized nebula 6543, it's brighter in it looks like tracing the hot bubble.
Yeah, it looks like that's the case in both nebulae. It's fascinating.
Yeah, so although you're estimating electron temperatures are very similar to the optical because it's where the density is higher, you also have some contribution from other plasmas in the emission.
Well, I think the opacity is very high at those low frequency, but I also noticed this in the Cat's Eye Nebula, this central region. But I will have a better quality image when more observations are taken, because it's not mosaic image, it's just one single observations, and then I will check it again, because I have another image which did not show this clearly, this center, but I will see in the future. I will see what comes out from this, because I was surprised. It should not be seen. The central region should not be seen in this, because the opacity is so high that we should observe only like on, I don't know, 5% of the radius. So
it is not that high, because we see the soft X range.
Okay.
These are very nice results.
Thank you.
So if we don't have any further comment or question, we thank Marcin. Thank you very much.
Thank you.
So we'll now have a 10-minute break for coffee and waking up a little bit more. So let's meet at 5 minutes before the hour. Okay. See you in a bit.
Excuse me.
Yes.
Jesús,